Good morning all of you, and today I am going to consider something called independent event. So before I go further, let me give you the feel of the situation. Let's say we have a simple space S and we have two related event A and event B, which is defined on the simple space. Okay, now we can talk about the probability of happening of A intersection B. So this is number of element in A intersection B in A. So let's say if two events has some common outcome, okay, or they might be related, they might not be related. So what is probability of A intersection B? It's basically number of elements in A intersection B by total number of elements in sample space. Similarly, if I tell what is P of A, it says number of element in A by number of element in sample space, and probability of B is number of element in B by number of element in sample space. Now there is a beautiful statistical connection between these probability if events are independent. So what does it mean to have independent event? It means the contribution of A intersection B in A should be same as contribution of B in the sample space. It means the part of B which is happening with A. So you see, if this is an event A, so once event A has happened, of course this part of B has also has happened in A. Okay, so what fraction of B is present in A? It is N A intersection B divided by N of A. And what fraction of B is present in the sample space? It is NB by NS. So if these two fractions are equal, we call events A and B are independent. Right? Again, I am repeating it. The fraction of B present in A should be same as fraction of B present in the sample space. Means it should be uniform distribution kind of. For example, let's say if you have A and B, and A contains 1, 2, 3 items. Let's say B also contains 3 items. So what is the fraction of B present in A? It's 1 by 3, right? Because 1 out of 1, 2, 3. Now what is fraction of B which is present in the entire sample space? So right now we have 1, 2, 3, and sample space contain 3 plus 2, 5 point. So it's 3 by 5. Okay, so clearly you can see these two events, these two fractions are not same, hence event A and B are not independent. What if I take a extra point? So again, fraction of B which is present in A is still this 1 by 3. Now fraction of B which is present in the sample space is 3 by 6. So still you can see they are not independent because they are not equal. Okay, I am coming to the physical feel of what exactly independence is, but before this I hope this example is clear. Let's take a numerical example to understand it more clearly. Okay, so till now what we have seen is probability of A intersection B is equal to probability of A into probability of B is a mathematical criteria to show these two events are independent, and this you can derive from here, because if N of A intersection B equals NA times NB with this fraction concept by sample space, so I can divide by NS on both sides, and this is nothing but P of A intersection B. This is P of A into P of B. So this is a criteria for independence. Okay. Now note that you may assume two events are independent in the following situations when they are clearly physically unrelated. For example, you toss a coin thrice. So the chance of getting head on the first one is completely independent of, it has no connection with chance of getting head on the second one. You can calculate the probability and then find P of A intersection B is P of A into P of B. That is another way to tell whether a function events are independent. Third way is when the question setter is already mentioning events are independent. Okay, so only 3 situations can appear in your JEE. Either throwing of coin and dice, they are unrelated, or use this mathematical definition, or question is already mentioning this. Now independence is a weaker property than being physically unrelated. Okay, so this is the most common confusion, so let me clear it out. For example, suppose if I like roll a fair dice twice. So we have fair dice containing 1, 2, 6, Again we'll have 1 2 6. So if I'm rolling a dice twice, the sample space will have 36 elements, right? Now let's define an event E1 as first roll is 6. First roll is 6. And let's define another event E2. I can keep on defining any events. Okay, so let's say event E2 is both rolls produce the same number. Both rolls produce the same number. Now clearly you can see, like if you apply that physical property of independence, so it feels like first roll 6 and both rolls same numbers are, you know, like physically related, because if both rolls are same number, it will also have you know, like 6 6, 5 5, 4 4, 3 3, 2 2 and 1. So this corresponding to event E2. Now again first roll is 6, correspond to 6. First dice so another dice can show 1 2 3 4 5 6. So we have 6 1, 6 2, 6 3 and 6 6. So mistakenly what you can feel like, okay, 6 6 is present here, 6 6 is present here, so these two events are you know, dependent event. Okay, now this is completely a wrong conclusion. So that's why I always warn you to solve these kind of problems and to get a feel of this after using this mathematical definition. So now let's calculate what is P of E1. So we have a simple space H containing 36 points elements. We define an element E1 and an element E2. Okay, so what is chance of E1? So how many elements are in E1? We have 6 elements. Out of this, one common element will be 6 6 for both of them. Then we'll have 1 2 3 4 5. Okay, so the chances is, probability of E1 is 6 by 36, which is 1 by 6. What is chance of E2? Probability of E2 is still 6 by 36, which is 1 by 6. Now what is the chance probability of E1 intersection E2? Means common between E1 and E2. So you see, common between E1 and E2 means first roll should show 6 and both rolls should produce the same number. It means the only possibilities of common between this E1 and E2 is, you can say, 6 and 6 is the only possibilities. So what is this probability? Is 1 by 36. And now you can clearly see P of E1 into P of E2 is giving me P of E1 intersection E2. So that shows, like, even if they were physically dependent, still mathematically or statistically these two events are independent event. Okay, so just with feel, if you are doing the problems, it's high chance you'll get wrong. What exactly is the essence of this? So as I have already mentioned, E1 is having 6 element, E2 is having again 6 element, 1 2 3 4 5, and we have only one element common between both of them, right, which is 6 6. So we have 11 element over here, right? Now how many elements are there in the remaining? Total is 36. 36 and 11 is 25. Now if you will see, like, how much part of E2 has happened in E1. So it's just 1 out of 6. How much part of E2 has happened in the entire sample space? Okay, so what is the contribution of E2 in the sample space now? So we have again 6 divided by total sample space is 36, and you see that exactly matches. It means the distribution is uniform here. In what sense I am telling uniform distribution? So we have one object, 1 2 3 4 5, 1 2 3 4 5. अब जो बचा 1 2 3 4 5 6 7 8 9 10 11. So you see, clearly the part of happening of event E1 in E2 is same as part of happening of event E1 in the entire sample space, or vice versa. Part of happening of E2 in E1 is same as part of happening of E2 in the entire sample space. If that is the case, then we call these two events are mutually independent. Clear? Now, other misconception is saying two events are independent is completely different to saying they are disjoint. The two events are never independent. In fact, two disjoint events are never independent. Let's say you have two events, A and B, they are disjoint, means there is nothing common between them. So what is P of A intersection B? That is definitely 0. And what is P of A? It's non-zero. What's P of B? Clearly you can see from this diagram is non-zero. So in this case, P of A intersection B is not equal to P of A into P of B. So two disjoint event can never be independent event. And that's again commonsensical, because suppose you toss up a coin and you are getting head. Now what is the chance that you got tail? That is already completely determined. It's dependent, because once you got head, the chance that you got tail is 0, right? Because either it will show head or tail. So getting head or tail on the coin is a disjoint set. Head and tail will make the entire sample space. Or let me make sample space correctly. If we have this sample space H, the flip of single points, either will have head or tail. Now you see, occurrence of head is automatically guaranteeing the non-occurrence of tail. So in this case, if there is nothing common between H and tail, these two event, so it's 5. But the probability of head is what? 1/2. Probability of tail is 1/2. And probability of happening both together is definitely 0. Okay. Or physically what you can tell, like the occurrence of one event is excluding the occurrence of other. तो ये तो खतरनाक रूप से dependent हो गया. So that is second important point. Don't confuse it in disjoint and independent set. Next is if you have 3 events A and B, C, A, B, C. Okay. So even if A and B are independent, B and C are independent, and C and A are independent, it does not necessarily guarantee A, B, C together will be independent. It means universal independence does not guarantee mutual independence. For example, PA intersection B will be PA intersection PA into PB. P of B intersection C will be PB into PC. P of C intersection A will be PC into PA if they are mutually independent. But that does not guarantee P of A intersection B intersection C will also be PA into PB into PC. It means even all 3 of them can be dependent, still 2 of them can be mutually independent. Now if entire system means AB, BC, CA and ABC. ABC means probability of occurrence together is probability of occurrence separately multiplied. So if this entire system becomes independent, then we have attained a universal independence in ABC. Right, so just pair by independence does not guarantee the universal independence of it. So I hope this is clear. Now it's time to take up one simple example, and let's take a question. Suppose EBA event in which the sum of numbers on 2 throw of a dice, sum of numbers is 6, and F be the event when the greater number is 4. Then check whether E and F are independent or not. Again, since we have 2 throws of dice, and total sample space consists of 36 points. Right? Now, if sum of number is 6, what is the chance of that? So 6 can come with 1 5, 2 4, 3 3, 4 2, and 5. So probability of getting E is we have 1 2 3 4 5. 5 by 36. What's the chance of getting F? Greater number is 4. If greater number is 4, so you can see like we'll have 4. Okay, 1, 4 2, 4 3, 4 4, and 4 5 is not possible. Now is 4 4 possible? Clearly not, because greater number should be 4. So here both are equal, so that I am discarding. What about 1 4, 2 4, and 3 4? It's possible, because when a dice is thrown twice, we want greater number to be 4. So we have 3 and 3 6 case. So यहाँ पे P of F we are getting 6 by 36. Now what is P of E intersection F? The greater number of 4 in sum is 6. So we have 2 4 and 4 2. So that becomes 2 by 36. So you can clearly see the P into PF is not equal to P intersection F. So they are dependent event. Okay, they are dependent. Again, what does it mean for dependency? If we have E and F, now the proportion of E which is happening in F, the proportion of E, which means this part, which is happening in F, is not equal to the proportion of E which is happening in the sample space. Okay? So in that sense, this is independent. So I hope this is entirely clear. Now one a small theorem is there which you can prove by yourself. If event A and B are independent, which means PA intersection B is PA into PB, then you can show event A bar B, event A B bar, and event A bar B bar will also be independent. Now it's not difficult to show, because what is P of A bar intersection B? So that you can see from the Venn diagram. If we have A and B, right, let's call the region 1, 2, 3, 4. So using set notation, what is A bar intersection B? A bar is 1, 4 and common B is 3, 4. Right, so A bar intersection B will be just 4. And what is 4? This region? This region is nothing but B minus A intersection B. Right, so it's probability of B minus probability of A intersection B. Now what is P of A intersection B? By definition of independence is PA into PB. So we can take PB common, 1 minus PA, and 1 minus P is complementary event. So PB into PA bar. So I hope it is clear. So you can see if P of A bar intersection B can be written as P of A bar into P of B. So hence A bar and B are also independent. Now that is again, it's obvious, because if the proportion of, if A and B are independent, it means the proportion of A, okay, proportion of A in B will be same as proportion of not A in the entire, like not A B in the entire sample space. Okay, so you can think in terms of proportion also, and similarly you can prove all the other. Let's take a JE problem, and that is a best problem which they have asked from independent event. So let mod of X denotes number of elements in set X, number of elements in set X. Let we have set X given as 1, 2, 3, 4, 5, 6, be a sample space where each element is equally likely to, where each element equally likely. Let A and B be two independent events associated with S. So A and B are independent events. I'm not writing full language in S, associated with S. Then the number of ordered pair A comma B means how many such events are possible, such that 1 is less than equals that B is less than equals mod of. What does it mean? Basically we have to find if the mod X is the number of elements in set X. So mod B is number of elements in set B, mod A is number of elements in set A. तो आपको क्या find करना है? We need to find like how many ordered pair of events are possible, so that number of elements in set A is more than number of elements in set B, or equal to, is more than equal to 1, and they are independent. So let's take a feel of the problem first, and let's feel with respect to proportion. So we have already sample space, and let's say we have event A and B. Now suppose if event A is having 3 points, okay, 1, 2, 3, and let's say event B is having 4 points. So 1, 2, 3, 4. So clearly we have a common point for both events. Now how many total number of points are there in the sample space? We have 6. So 1, 2, 3, 4, 5, 6. So here if I'll ask what is the proportion of A in B, so proportion of A present in B is 1 by 4. So proportion I am writing, proportion of A in B, prop of A in B is 1 by 4. Now what is proportion of A present in the sample space? Proportion of A present in sample space S, we have 3 by 6, which is 1 by 2. So proportion of A in B is basically this part divided by B. Now proportion of A which is present in the sample space is 1 by 2. So since they are not equal, so this picture corresponding to this picture, the events A and B are not independent, although it is satisfying this condition, because you can clearly see mod of A is having 3 elements and mod of B is having 4 elements, so it's not satisfying this condition. Okay, so anyway, let's take another example when it satisfies a condition, like number of elements in A is more than number of elements in B. Okay. So although it satisfies the conditions, because the number of elements in A and B are same here, we have 3, okay, and we have so what we can see is, although the given condition is not satisfied, so I've just taken one random example where corresponding to this case mod A is not greater than mod B. So let's take an example where I respect this condition and then try to see what is possible. So if A is having, let's say, 4 elements, 1 2 3 4, and B is having 2 elements, so let's say 1 2, so we have total 5, so one element will go neither in A or B. So this is set A and set B. Now again, what is the proportion of A in B? So that's 1 by 4. Now what's proportion of A in the entire sample space? Is 2 by 6, because sample space contains 6 points and we have 2 points. So clearly 1 by 4 is not equal to 1 by 3. So you see, like, this is an example where A and B are not independent. So if A is having 2 elements and B is having 4 elements and one element is neither in A and B, this picture will not work. Let's take one more example. Suppose if B is having 1 2 3 4 5 elements and A is having only 6 elements. Okay, only one element. Then again, what is proportion of A in B? It's 1 by 5. What is proportion of A in the entire sample space? 5 by 6. So clearly it's not equal. I say you can experiment, okay, but of course, like, we'll not keep on doing this problem in a childish manner. So is there a better way of doing this? So whatever I've done so far, except the first case, because the first case is not in sync with the given Guardian set. Now we can formalize this, because let's say if we have set A and set B, so now I can tell if A and B are independent, so P of A intersection B will be P of A into P of B. So N of A intersection B divided by sample space is NA and B divided by NS whole square. So 1 and NS will get cancelled. So I want number of elements in A intersection B into number of elements in sample space is NA into NB. Now in this case, we already know number of elements in sample space, because this is going to be 6. So we will get number of elements common to NB 6 times will be NA into NB. And now we can do case making, right? Now we can do case making.